Welcome back to Computer Science 4303. Today I have a very special guest with us, Nathan Sturtevant, who is currently at the University of Alberta, but who's worn many AI-related hats in the past. So welcome, Nathan. Thanks for being part of the class.
Thanks for having me today, Dave. Glad to be here.
Yeah, it's awesome to see you again. It's been at least since the pandemic before we've really had a chat.
Yeah, it hasn't been in person for years, so that's, I think, where we used to run into each other all the time.
Definitely. So if you could give yourself the sort of intro that you actually deserve. I know that you've had lots of academic experience at different universities and industry experience and AI code published in actual retail games. So tell us what you want the students to know about yourself.
There's a bunch of things I could say, but I just say, so currently I'm a professor at the University of Alberta, and I'm also the director of the Alberta Machine Intelligence Institute. And so I just have to plug that a little bit. Within Canada, we have 3 institutes nationally as part of the national program for AI, and we have one of them here in Alberta. And so we're really proud of all the researchers we have here doing work in quite a broad range of AI. Personally, I also got started writing shareware when I was in university, and had the opportunity to work with Bioware on Dragon Age. I'm currently working with Inflection Games on their upcoming game Nightingale. And so had some experience in industry and had, of course, lots of experience in academia. And I guess we'll get to talk a little bit more about some of those things today.
Great. And I also heard you talk about AMI, A-M-I-I. They have an event coming up if you want to plug that real quick.
AMI has, if you go to ai-week.ca, we have an AI week coming up in the end of May. And this is an opportunity for training, for getting to know other people in the AI field, up and coming. We're inviting people from around the world, but we have a student talent bursary that's coming in. We're going to have an academic day of talks from many of our professors and others about various aspects of AI, and a lot of other training and other interesting opportunities there. So if you're interested, ai-week.ca.
That's awesome. Yeah, I'm trying to get there myself. It would be great to see people from Edmonton again. Just a quick note for people who are in class who may not know. So I did my PhD at the University of Alberta from 2009 to 2016. And were you a postdoc then, Nathan, or were you?
I actually finished my postdoc, and I was I had some other title.
Okay, doing research at least.
Yeah, I was like a research something, and then I was also had an adjunct status, so I could co-supervise students. And that was until 2010. So, I saw you coming in, and then I came back here in 2018.
Great. So yeah, I guess we had some notes on what we wanted to talk about. I guess one of the first things I wanted to get your opinion on, or if you feel like talking about specific work that you've done first would sort of add more context to that. One of the things I tried to sort of explain at the beginning of the course and throughout the course is sort of this difference, or at least perceived difference between more quote unquote academic AI, like mainly working in algorithms, fundamentals, that sort of thing, and game AI, where, you're given a task to do by a game designer and you just have to sort of get that done. Can you talk about any of the sort of, like I said, different hats you've had to wear and how development of academic AI might be different from industry game AI?
Yeah, I mean, there's a lot to that, and there's a lot of histories around conversations that have happened around that subject. And so I'll give you a little bit of my take on it. And so one thing to say is that if you go back 15 years, for instance, there was a much greater divide between industry and between academia. And I think there was perception, whether this is reality or not, but I think there was perception at the time from the games industry side that academics basically didn't understand the constraints of the games industry. And we're just coming in and saying, well, we're experts in AI, we can tell you everything you need to know. And there was just a disconnect in what does it take to make AI for a game? What are the goals of AI for a game? Are we trying to crush humans? Are we trying to create an entertaining experience? Are we trying to create something that could be understood? So there's even philosophical implications to like, what is the goal and why is that our goal? Very often in AI, the question has been, how do we answer fundamental questions of intelligence? And so the motivation there is often an understanding or a simulation of something where that is done under constraints that are very different than exist within the games industry and have a very different purpose. We're trying to prove something about the world, or we're trying to prove that we're smart and we can come up with good models. There's lots of different things that are going on and motivating different pieces of research. And oftentimes we abstract away some of the costs or some of the realities of getting a system tuned that just simply don't exist within the games industry. So just to give some example of that, when I went to work at Bioware on Dragon Age and on the pathfinding system there, we had the core system. Like I had already designed the core pathfinding system and implemented it academically. I had published papers on it or on the concepts. But when we went to like actually make it work in the game, then there's a whole bunch of things that no one really cares about within academia. Maybe that's a little bit of an overgeneralization, but there's a lot of things there that they don't show up in a chart in a scientific paper that really, really matter if you're going to actually ship a game. And so you just have to be very aware that there are those differences. And some people said to me, well, those sorts of things I simply do not care about. I don't want to ever think about those things. So researchers in the field have said things like that to me about some of the things we did that I did to make the pathfinding engine work well in a commercial ship title. And so, you just have this reality of some people do care and some people don't. There's some academics that really do care about such things and making sure that they can really work in practice. So there can be a divide there. But what we've also seen in the last, let's say 5 to 10 years, but maybe particularly in the last 5 years, we've started to see, I think we see more people from academia, like getting a master's degree, understanding the academic side, and then going into the games industry. And so I think there's a little bit more communication back and forth. And that I has really helped. The other thing that we see is that we've often thought about AI systems in games as like NPC character AI. But there's a lot that goes into games, and as the games industry has grown, there's a lot in games that is much broader than just like NPC character AI. And so we can think about, if we think about free-to-play titles, and you think about how am I doing my marketing, how am I making choices of the offers that I'm going to make to players, retention of players, and things like this. There's obviously a discussion there we could have about the ethical practices that are involved there, but there are AI systems that can analyze players, that can analyze the big data that we get. And so that's an application of actually a little bit more, directly coming from traditional AI, being directly applied in the commercial aspect, a little bit different from the game design or the characters that we have. So as we start to see AI in games, there's actually starting to be quite a broad range of ways that can look beyond maybe just what was 10 to 15 years ago. Most people were mostly talking about NPC behavior. And when we think more broadly, then we see other applications.
Yeah, that's a good point. And I think that, my stuff in particular, since things like, AlphaStar have come out and sort of taken over the, as the world's best StarCraft AI. And so my research sort of had to pivot. One of the things that I've been focusing more on is something like, okay, well, I remember back when I gave a talk at GDC, I was giving a practice talk to Dave Mark. And one of my slides said that my search ran in 80 milliseconds. And he said, take that off the slide because no one will take you seriously. Right? Like 80 milliseconds is a lifetime to an actual game programmer, but in an academic paper, that's actually pretty quick for a search to run, or at least it was 10 years ago. So that idea that game AI doesn't have the cycles to spare it's been one of my recent arguments, is that, well, like you just said, traditionally it's been viewed as in-game AI, like running in real time, controlling a character. But I think more things like offline game balance if you want to say balance StarCraft, right, you could do all sorts of AI there that might take a year to run. Well, maybe not a year, but a few hours to run, that could give you insights about your game offline. So hopefully that sort of thing is more prevalent in the future, especially with things like QA. I'm sure. I think Julian Tegelius is part of a company now that deals with things like
Model.ai.
Model.ai, where they, instead of hiring 1,000 people to try and get Mario out of bounds, just hire one AI system to try and get Mario out of bounds, and then try and do bug fixing and stuff around that.
Yeah, and there was actually a great talk at the GDC AI Summit, maybe 7 or 8 years ago now, by Paul Tozer, where he was talking about how they were building an AI system. And I think there's an article out there available as well. But they built a system that basically every night would just play the game and come back and report balance information. They used genetic algorithms to tune how the game was being played. And they found it very, very successful, that it vastly accelerated the design process. And so, there are opportunities there, but you have to start to set up your systems from the beginning in a way to make that possible and really have that as a goal. And not every company does that when they're developing a game. And so, some of these things are not feasible in all circumstances. But there are, if you're working on a particular game of a particular genre or particular constraints, there may be some really interesting things that could be done there.
Yeah, definitely. And it sounds like sort of the way you've described it is that the system is kind of working as intended, right? Whereas, 20 years ago, game AI as an academic pursuit really, it's been 50 years old if you talk about things like chess, but video game AI in particular really started to become more of an academic pursuit. And then, academics, like you said, are far less constrained in their ability to, run a big experiment or not have memory constraints or system constraints. And then once those people figure out some cool stuff, maybe then the game industry takes note of that, and things like, recent advances in machine learning have gone into some games. And so it's kind of cool that, it's kind of like the sort of real world research side of things, where people are, researching these maybe cancer drugs or something like that, and then they eventually get they put on the market in a real setting and used by people. So it's kind of cool that that's happening more. Academic and industry AI are sort of overlapping more now.
Yeah, and I have a student, Kristen Yu, who's working more than I am with Inflection Games. And so Inflection Games is a local studio. It's formed out of a lot of ex-Bioware people. And that's how I knew many of the people who were there. So I've been working with them for quite some time. And if you look at what Kristen's doing in her PhD, what you can see is that she's using her research to inform what she does in her work there, but what she's doing in her work there is also informing her PhD. And so when you have people who have those opportunities to be sitting with one foot in industry and one foot in academia, then there's a lot more flow of ideas back and forth. And I think that's really encouraging for having a positive impact on industry and having good collaboration, so that we're not just coming in and telling them what to do, but we're learning from them, they're learning from us.
Yeah, I was really lucky to be able to do some of that with Prismata stuff at the end of my PhD, which I've already talked about in the class. But it was really cool to see that, what does the game company care about versus what you as an AI developer care about. And I remember at one point, you're going back and forth on requirements versus what you can actually deliver. And I think the marketing team called me like a diva at some point because I didn't want to use machine learning because I didn't think it was feasible, but they wanted to market it as that way. And it was interesting, all these different things that aren't present in academia come up, and it's a really good learning experience.
Absolutely.
So speaking of actually using AI in games, we talked a bit about what we were going to speak about before this, and you're, as far as I know, one of the world's experts in pathfinding, and you've done a lot of work in games with pathfinding, but you talked about representations and how they matter. And so in this class so far, we've talked about everyone at this point, it's a 4th year course. They know what a graph is, and they've done some breadth first search and depth first search on a graph. In a previous course, that's a prerequisite for this one. They've done A*. We've talked about weighted A*, those sort of searches. But most of that up to this point, at least in this course and the prerequisite, it's all been done on grids, because this is sort of a video game course. Lots of video games use grids. I had a whole lecture on how StarCraft uses grids for things like walkability and building tiles and stuff like that, and whether you can fly or walk and all sorts of things. So what do you have to say about representations and
Yes, so this is always a starting point. There's actually another starting point I have in conversation, which is, so I'll just mention this because I don't know if we'll get back to it, but is that oftentimes people think of pathfinding, oh, that boring pathfinding stuff, that's just the pure algorithmics. I actually view that pathfinding is sort of a fundamental system in which the rest of the game is built upon, and the rest of the game AI is built upon. And so if you're not thinking about how your higher level behaviors depend on what's being done at the lowest level of pathfinding, then there's going to be a disconnect there. And we were recently having a conversation with some people in industry about, actually probably about a year ago now, but about how, that's a really important view, is that, pathfinding, although it maybe seem like, oh, it's just algorithmics. And we'll talk a little bit about this in what we're doing with Nightingale, about that need. But so at the bottom level, we can start to talk about representations. And historically, there's sort of been three really common representations, which are grids, waypoint graphs, and nav meshes. And nav meshes are work really well, are really popular. Grids are actually a special case of nav meshes because every grid cell is basically a portion of it's basically a mesh. It just happens to be entirely square and uniform across the environment. And so there was this argument when nav meshes came out that they do this great job representing the world, and they're just sort of uniformly superior to grids in many ways. And some people expected grids to sort of die off, and yet they haven't for many different reasons. And even if you look at the implementation of the engine that most people are using for doing pathfinding or for building nav meshes, what it does is it actually divides the world in grids, and then from those grid cells, it makes them into nav meshes from that. And again, we rely on that a little bit in Nightingale for the pathfinding in there. But there's actually a fundamental point here, which I want to step a little bit back. And when I'm teaching my lecture, for instance, in the class I'm teaching this term on which is a video game, it's an intro to video games. So we get one lecture on AI. And one of the things that we talk about is, starting with AI, is like, why does pathfinding fail? And you can get lots of videos that show pathfinding systems are, like the characters get stuck in walls, they fall off of cliffs, just in general, they fail in interesting and unexpected ways. And the question is, why is this happening? And the reason why is it doesn't matter if you're using a nav mesh, it doesn't matter if you're using a waypoint graph or a grid. If your game, and many games do this, they're running the game actually based on physics. So they're using a physics simulation, like I have a capsule around my character. When I move that capsule around, that's actually, there's some physics simulation that says what I can and can't do. And yet when I have a pathfinding representation, that physics representation actually isn't efficient at all for thinking about planning and pathfinding. And so there's a disconnect there, basically, in the physics of running the world and the pathfinding that we use for doing planning in the world. And the bigger that disconnect, basically, the bigger space there is to see errors crop up in your pathfinding. So there's a really interesting talk by Casey. I'm probably going to mangle his last name is Mutori or Murutori, something like this. And I've talked to him a little bit about this because I found a bug in the pathfinding and in the witness. We may just be in the character controller, but they actually worked really hard to actually get the physics to directly align with the character so that you wouldn't get these sorts of bugs within the game itself. So if you're interested in more details on that, you can go find his talk online. But this disconnect and this question of, what is actually running characters in the game? If it is physics, then if my pathfinding representation isn't directly physics, then there's going to be some classes of bugs that have the potential to show up in my game. Mm-hmm. And we have to be aware of that. And then sometimes we make the choice and we say, what, we're just going to be perfectly willing to live with that. We're going to do our best to compensate for that. But every game, there's a limit. We've talked, this is sort of the game AI versus academic AI. There's a limited number of resources that can be put into the game to making things work. And sometimes you just say, that's not a trade-off we're paying for. Another example of that, which is very related, is that I give you a path. So we have these layers of, how do I have to find a path, but then when I get a path, I need to execute that path. And how do I execute that path? Well, executing that path, which is often called locomotion, is based on the animations that I have for my characters. And then where do my animations come from? Well, there's some machine learning animation libraries that have been used by companies like Ubisoft, or sometimes we have designers that are designing those animations. And so if we start to think about that hierarchy of like, I give you a path, I try to follow that path, and we start to think about where do my feet land in the world? Do I have foot slide? And what are the consequences of that? So then again, we get to this case of like some AAA games have said, we are going to make that movement be absolutely physically as realistic as possible. Other game companies say, you know what? There's going to be some things here where there's going to be some foot slide in the world where my character, isn't perfectly animating as if the physics are running that character in the world. And we don't care about that. We're willing to take that compromise because of the constraints that we have. So we have to understand that this sits at the very bottom level of pathfinding in games, and all the technologies sort of run on top of them, and different games with different constraints, different programmers, other things like this, the engines, they all basically sit in that space and make decisions about where those things are going to exist within their game.
And I assume it also affects things like even level design, right? If you've got a bunch of, say, small rooms that you want to build, but your AI system may bug out in small rooms or do lots of like turning on a dime or something like that, maybe your game all of a sudden doesn't look as well. So I'm sure, like you said, if you have an AI script or a system that's even wants to do something like attack the player, well, it's got to get to the player first, right? So it really is all built on the foundations of that. And I mean, sometimes we want to call our work more important than other systems. It's not more important, but it is really foundational in that it has to work correctly in order for other systems to work correctly. And you mentioned the physics system messing up AI in older games. Like, for example, we're using this 23-year-old game in our course called StarCraft. And in the original version of StarCraft, it's not so much physics, but the animation system that screws up things like pathfinding and attacking. And all these things are like tied down to all these hard-coded frame amounts. Like, you can't move a Dragoon for 7 frames after you've started an attack. And it's like, why? It's so annoying. And you get all these weird, buggy behaviors in your game. But humans don't seem to notice those as much as AI programmers do. And it's something that may be really annoying for an AI programmer the human doesn't even notice. So we didn't really drill down into representations, or say, for example, being really byte optimal when it comes to those representations. Could you talk a little bit about how, in terms of your academic work versus your industry work, how optimized do you get with your data structures? Do you always try and get down to that bit level, or are you sort of okay with integers where a char might do? Is there any sort of story there that you could tell?
Yeah, I mean, so this is always a trade-off, because what happens is when you write a software system that is flexible, so I want to run a bunch of different experiments, try a bunch of different things. When I add that flexibility, then it basically takes away some optimization or level of optimization. So I can use this a little bit to segue into some of the stuff we did for Dragon Age. We'd been working on ways of doing abstraction and doing refinement for doing pathfinding in games, doing it incrementally so we could be able to have a character start moving immediately, even though an entire path wasn't planned. Features that we wanted like this. And when I had implemented it, basically I had this graph data structure which represented every node. I mean, and it was if you think about the overheads that were in there, they were massive, like 100 or 1,000 times overhead, pointers, memory allocation everywhere. It's a complete mess, at least from an optimization perspective. But in practice, of course, once you allocated all the memory, it still went pretty fast. Mm-hmm. But when we sat down with Bioware and said, okay, these are the constraints we need in the Dragon Age engine. These are the decisions that have already been made, and these are what we're going to be working with. This is the way that memory is laid out, and this is these are going to be the sizes of the world, and we need to design something that's going to fit within that. We then hand coded basically every single bit of where that memory was going to be used to be able to optimize and say, we're going to exactly be able to fit, basically it said you don't have any memory. They said, okay, great. Well, we're going to use 1% extra memory, which you can afford. And we've got this highly optimized piece that we can then throw in here. And it's going to, we're going to be able to do the pathfinding 10 or 100 times faster than the systems you have running in the game right now.
That's great.
yeah, so that was this thing of like, now we sat down and made a whole bunch of decisions. So they're like, the way that we did abstraction was grid-based top to bottom, where previously I wasn't doing it grid-based, I was doing it just graph-based. And that saves a ton of memory. It avoids having to have pointers. It avoids a bunch of memory allocation. So that's the type of things you start doing when you really want to get things working, very, very efficiently.
And just as a reminder, if you did have anything to show about Dragon Age, you can feel free to screen share at any time. I guess that's a good segue into that topic.
Yeah, so I'll talk a little bit about that. So they were building the game. They came to a point, simultaneously they started building the game, and then made some decisions about how to run things, and then sort of got stuck. At the same time, I was doing research on exactly the problem that they had of this doing really fast pathfinding in grids. You have to understand that this is my work started back in 2003, 2004, when I started as a postdoc here. And at that time, pathfinding in games was universally atrocious. You couldn't do a lot of things that we just sort of take for granted today. And so anyways, I'd been working on this, and then they sort of came to us and said, can we make these things work together? And we were able to do that. And so I'm going to start here by just showing, I'm not going to talk too much about how we do this.
Just really quick before this, just some context for the students here. So Bioware, a very famous game design company, made Dragon's Age as well as Mass Effect. They're located in Edmonton, which is right next to the University of Alberta, which is where Nathan was at the time. And so they were able to partner with one of the local universities, which is great. So Nathan, one thing that I saw when I did this a couple of lectures ago is that there may be an option somewhere to optimize your screen sharing for video.
Yeah, let me see.
Otherwise, it may be a little bit choppy.
Here we
so
go.
we can take a minute to do that.
Option. I use this when I'm teaching, but I hadn't turned it on here. Okay, that's on. The video isn't too long, but hopefully that'll.
Sure. I'll let you know if it's unbearably choppy or anything like that.
Okay, and let me see if I can get this piece moved out of the way so that it doesn't cover the screen. Okay, so so what we wanted to do is there's a grid representation for the world. And so this means at the lowest level, this is a very early prototype where we're basically testing that things work very well. At the very lowest level, there's a grid. And the grid is then abstracted into what we call sectors and regions, but basically you just get big squares in the world, and you see which components in each square can be reachable from each other. And then once you can see what is reachable from one portion of to another, then you basically build a high-level connectivity graph of how you can move around in the world. And then we do pathfinding in that high-level connectivity graph. Once we do that high-level pathfinding, then we actually start walking in the world. And to do that, we then do a refinement step-by-step of each of the segments of the high-level path. And we'll actually see some of the details when we talk about what we're doing in Nightingale now. But this video will show us many of the features that we had. So what we have here, can you see my mouse?
Yes, I can.
Okay, so we're going to zoom in and see this in a second. This is just showing a partway through the clip. So we have a character here. So these are just textures that weren't defined. So we have this texture not defined text here. The character didn't have any of its textures working that day either, so that was perfect. So we didn't reveal anything about the game early on. And what we're going to see is the character is going to be asked to walk from here to here in the world, which requires like walking out of this room, walking around here, walking over down here and around here. And if we look at the low-level grid, we're looking at like maybe, I know a few thousand, 10,000, I don't know the exact number here, but there's quite a few grid cells that you'd have to search to find this path. And by using this abstraction, where you can see here, the path is made up of only a few dozen segments.
Are we seeing that grid there in the dark gray color?
Well, so these are obstacles going around here. Each of these squares here is one piece of the texture, which may be aligned with that grid, but I don't remember exactly. The texturing can be a little bit different than what the low-level grid is. But you can think of each of these sort of green segments where we see this texture not defined as being like one cell of the grid. That'd be a fairly accurate representation. And then when that text sort of goes on both sides of a wall, you'd basically say, well, this grid, this large scale grid is divided into 2 different regions. And we just know that you could be on either side of that region when you're doing the pathfinding.
And so this pathfinding system, was it single agent?
So this is a single agent system. Only single agent was put into the game. They've explicitly said we have an idea of how to do some of the multi-agent things. And in general, the spaces in games are divided so that you can do local control. And we won't really probably have time to talk about that today, but you can do local avoidance. And there's a whole bunch of ways you can do that. Orca is sort of something that's become fairly popular, but there's dozens of ways, and some work better than others. Some are more robust. You can find articles and talks about that. But basically, it's local avoidance that say, look where they're going, look where I'm going, and try and find a heading that can slightly adjust my path to avoid other characters. But we're not going to think about any of that here. Some of that was put into the game. We have much better ways of doing it now than we did when Dragon Age was under development. And so what we're going to see here is I'm going to play this video, and what we'll see is I'm going to click over on this portion of the screen, which is right over here. You're going to see this path is incrementally being planned while the character is already moving. And then as we start moving in the world, what you'll start to see is that some of these sharp corners that exist will incrementally be refined as well. So let me just go ahead and play that, and we can watch. So here, this is the start. Yeah, this is the goal. We're going to go right there, and we can watch this. So I'm going to zoom out. We're going to click over here to give my goal. And then as we watch the path, particularly over here, we can see that on here, the path is being refined incrementally. So if I'm someone who spams the mouse all the time, up here we'll see it smoothed again as I get close on that path. If I'm spamming the mouse, then I don't spend a lot of time doing this sort of making a really, really, really high quality path for you.
Mm-hmm.
And then you just click the mouse again and I start the process all over again. But by interleaving the planning process and the movement, then I can delay a lot of that planning process until later on when it's looking more likely that I'm going to use the full path. So if we see this final path, it's fairly smooth here, whereas if I jump back quite a bit earlier in the process, we can see that there's some pieces here that were actually not smooth at all, but had a chance to be smooth once the character got along the path.
In terms of, so in our class, you spoke a little bit about this. I used the terminology pathfinding versus path following, but path following, you said, is locomotion in the game AI world. So in our class, for example, we would do things where we would do all of the pathfinding in a grid, but then use something like steering to do the path following. And so the path you calculate is quite jerky, but the path you walk is actually quite smooth. Did you do like anything like this here, or is it all done at the pathfinding level?
So it's done in both, actually. And at one level, right, you can do this. In fact, so this is a slide out of a longer talk. It's like an hour-long talk. But if we look at this, then what we see is that you can do some of this local avoidance. But when you have like big discontinuities, like where I'm really making sharp turns to walk around things, then this isn't always going to be able to recover. So the point would be is that, every layer we're trying to do a little bit of adjustment. The animation system is putting some constraints on, the pathfinding is trying to produce the best path. So we've got the pathfinding, we have a smoothing layer, then we have like a locomotion layer or just a path following layer that's trying to do some things. There's another piece I put in, which was like the characters, when they hit a turn in the path, we're turning their heading 100% in one frame. And I just changed it to like interpolate 90% in one frame or 80%, it's a value you could set there. And it made this huge difference in how smooth it felt as you walk through the world, just to take like 2 frames to turn my heading instead of 1 frame. I still moved along the same path. So you gave up maybe some fidelity to where your feet were standing, but there's a totally different feel in the game when that change was put in that just made it feel like, hey, I'm walking smooth through the world as we go across some of these pieces. So these are the types of things that sort of exist and are accounted for at all levels of the pathfinding, pathfinding, navigation, locomotion.
So what algorithm was being used here?
Well, ultimately, this is A star, right, or weighted A star, top to bottom. Now we're using, when we build the abstraction, what sometimes people want to call this a different algorithm, but it is, it's just A star. So you've got the abstraction, you do A star in the abstraction, you're doing refinement, you're doing local A-star searches or weighted A-star searches, but it really is just this core best first search, top to bottom.
So I'm trying to just, you know, make it a little understandable for the students. So is it the case that this path smoothing is something like you're starting out with bigger squares for your grid, and A star is done on that, and then as you're moving, the squares are getting smaller, so your path is getting smoother, or is there more?
No, that's a good question. Actually, what's happening is that we know that the path itself is on real valued coordinates. And so what we can do is we can look at segments of our path. And as we look at our segments of our path, we can say, for instance, up here, this is about to happen. So I can just show it to you. We actually look at this segment of a path and we say, you know, this segment of a path is octile optimal, meaning that it looks like an optimal path, given that you're on a grid. And so we actually look, for instance, for segments that look like that. And then we run a ray trace that basically says, well, can I just go straight between the beginning and end of this? The answer is yes. And so what we see here is a few frames later, that just gets replaced by exactly a straight line, where the path before was basically, it was the optimal path on a grid. We say, hey, if I have an optimal grid path, let's see if we can replace it with an optimal path in open space, knowing that we can actually walk in open space.
That's great. And so in terms of just the actual implementation of this, without going into too many details, typically in games or in your experience with games, are you running the pathfinding in a separate thread, or are you like interleaving it inside the main loop? How is that being implemented?
So in Dragon Age, and I think for most, well, I can't speak for most games, but for many games, what you have is, you know, we've got a certain amount of time that's allocated for the AI. We're going to go through the characters and ask them what do they need to do for their updates. Depending on your engine and other things like that and the different optimizations. But then what typically happens is you come to a character, we say we need pathfinding. So we go off and say, okay, you've got up to a millisecond, go get me a path. Or in the case of Dragon Age, what it was is, hey, you're in the middle of doing pathfinding. Well, that's great. Do the next step in the path that you need to do. So the next step might be, do another step of smoothing. It might be do another step of planning. It might be that you're doing your high level planning. We ended up with actually 2 levels of abstraction. So you do a very high level path, and then you do like another abstract path under that, and then you do your concrete path. So you might, over the course of several frames, you might be doing these different steps, but they're usually not run in parallel, because here we're reusing the memory that's being used. So the memory that's within the search itself is being reused. And we don't want to have, at least in Dragon Age, we didn't want to have like multiple copies of the memory for doing pathfinding. We've got one chunk of memory, and whenever you do pathfinding, you reuse that memory over and over again.
And something else I tried to instill in the students was, before you go jump into developing an AI solution for something, you really need to know the properties of that environment. So one of the things you said that was really important is that this is a single agent, single path sort of thing. But if you were to, be put in charge of the pathfinding for, say, Diablo or Path of Exile, where you might have 1,000 NPCs trying to get towards the player, you probably wouldn't, do 1,000 instances of A star. You might go with something like, I don't know, BFS or a vector field or something like that.
Yeah, so a vector field, and I won't say anything about Nightingale, but you can do a reverse search. If everybody's attacking the player, you start at the player, you do a reverse search out, and that gives you a vector field of how do I get to the player, and everybody can follow those paths. Basically, you can compute them all simultaneously. And then we can do efficient pathfinding. Or if we know that, like, hey, there's something like a portal on a map that everyone needs to go to. And so we can actually do like one backwards search from that portal. And now everybody has really good information about how to get to that portal. And so all the requests, it may be that 90% of your requests are actually going to and from portals or something like this, or between portals. And if that's the case, then, it may not be, but if you have something like that, where you have like very common destinations, then you can actually pre-compute something like that and save massive amounts of time by not having to redo it over and over again from all the different characters in the game.
So I feel really good now, because assignment 2 in this course was we created our own grid-based navigation mesh and then did a backward search vector field. And so the motivation for that was, we're these sort of action RPG type games, And then for bonus on that assignment, you could do a little particle system, and the particles would follow the vector field toward the player. So it's good that someone else out there who has more experience than I did said that that's sort of, you know, what they might do in a game, because then the assignment becomes more relevant. Cool. So if you wanted to talk more about Dragon Age, feel free, or if you wanted to transition into your more recent game, Nightingale, I think it was.
Yeah,
Yeah.
so let me use this as a transition, because you talked about this, which is really important, which is this question of understanding what are the constraints in the game. And so in Dragon Age, the idea was, well, the world is going to be static, and we just have to deal with that world as it is. But in reality, of course, the world wasn't static. And it ends up we had a tiny bit of memory where we could represent some things that were dynamic in the world. And I think I'm going to thumb through these slides if I actually, so this is showing actually, Dave, what you were talking about a minute ago, like I can just follow these points by using local movement. I can get more or less a smooth path by doing this. But we may have other constraints. So for instance, in Dragon Age, there's traps. And we wanted to be able to avoid traps, or I wanted the characters to be able to avoid traps, which is actually I'm going to show here. And so we wanted to be able to say, like, dynamically, I discovered that there's a trap in the world, which this is actually showing the underlying grid, and the traps on them are, we're going to say we want to avoid things like traps. And so we can watch a character here. We've detected the trap, so we'll walk around it. We can go back and we can disable the trap, and it changes the underlying grid. If you look really carefully, it's probably not visible in the video, but there was a slightly different color here. When I disable it, then the color actually changes back to this green. There's more of a cyan color that shows how we know that there is a trap in the world, and that it's that it modifies the grid. So we had a few bits that said, like, we can do a little bit of modification of different types of terrain to say that, I want to try and walk around this if I can. But these were sort of very local modifications. We did them around player characters or non-player characters, and we also did them around, so this is from much later in development. We also did them like if you cast a large spell, then that spell would actually mark the ground and characters would try and walk around it. The designers turned this off in Dragon Age 2 because the characters, the NPCs were running around your giant spells and saying, oh, I don't want to run through that spell. But they did something which is really good. This is what they told me, that they also said they're going to change the animation. So instead of walking into a wall of fire, they changed the animation to be more like asteroids falling down, particles falling down. So there wasn't this clear boundary between like walking into a wall of fire, which looks really dumb, versus, well, there's this big area effect. Now I'm more willing to walk into it. But so the thing here is that we didn't have any distinction between our different types of representation of different types of terrain, different types of character. And we really didn't have a way to say, hey, something really just changed about the terrain. The terrain was expected to be completely static. And so this is something we wanted when we sat down with the designers. And just to say this is really important, is we wanted to sit down. When I started working with Nightingale, we said, well, we're not quite sure, where we're going to be able to apply different work, what's going to be relevant for the company, but we know we can work on pathfinding. And so let's start just by talking about pathfinding. We'll use that as a way in, and then we'll just see what comes from there as the game gets further along in development. So the first point that came out was that the world is more dynamic. We have a rich world. We have many different types of characters. Some of the constraints and other pieces around the world about the world have changed since our initial conversations. But we sat down and really talked about what were the priorities for the pathfinding system, its capabilities. And when we had that discussion, then we started to talk about what could we do to make sure that the pathfinding system would support this in the best way possible. And this has already been published, so I can talk about this freely. So one of the things that was really in some ways was a problem with Dragon Age was that the representation was static. You built it when and this had to do with memory and other constraints, but when a map was exported, then the map with all the doors open and everything unlocked was exported. And then that's the map that we use for pathfinding. And so the first piece is like, well, we'd like to have a world that we can handle changes in that world. And then the second thing is that our world is a richer world. So we wanted to make as part of the representation, the type of terrain that exists in the world to sort of be first class in the representation. As I said, like we had a few bits where we could say, you know, walk around a trap or walk around a spell that's been cast. But we really wanted to say that the type of terrain that exists in the world and the way I'm going to interact with it is going to be sort of is first class in the world. And we're going to directly represent that and directly be able to reason about that instead of indirectly representing it or indirectly reasoning about it.
And sorry,
And
Nathan, this is a single player first person or third person type? Does it?
so you can take a look at the trailer for it.
Okay.
You are it is a multiplayer game that will be played cooperatively within the world of Nightingale and the Nightingale universe. And so yeah, it is a cooperative game that's shared. So the company Inflection Games was previously owned by necessarily I can't say the game. Improbable. Improbable did a lot of basically did you know, having big servers that can run and simulate giant worlds. Improbable has spun off. Inflection Games are now owned by Tencent and funded by Tencent. So there's been some changes there. But yeah, it's a multiplayer game where you're going to play together with your friends, and it's a survival crafting game. So that's a little bit more of that context.
Yep.
And so what we're thinking about in our world is that and the other thing is that the representation that's being used is a navigation mesh, and that's in Unreal. That's sort of a standard representation that's being used. But I'm going to show you here this demo that is working on grids underneath. But essentially, you can replace, because the recast system is by Mikko Manonen is being used in the game. The recast system divides the world up into big grid cells, and then it does triangulation of those grid cells and makes a nav mesh out of that. So we basically can use those large grid cells that are already being used in the game, even though it's a nav mesh, and directly do abstraction on top of that. So what we see here is a representation of the world. The world's empty, so I can turn the abstraction off. It's an empty world. And you can see here, there's grid cells, and we're just showing that there's pathfinding available. The world's entirely free. And then what we can do is we can say here, and this is designed to be very dynamic, is I can say, like, I'm going to draw a path into the world. So I can come up here, and I can just draw with my mouse and say, okay, here's a path that's going to guide me through this world. And what you see here is the abstraction is being deformed so that there's basically one abstraction that represents the path in the world. And I can turn that off. But basically, as the path goes through here, then there's a separate representation of the terrain of the path from the representation of the terrain of just the open ground. I could go in here, for instance, and I could put water in. And I could say, you know, I'm going to put a big body of water over here. And what we can see is that the abstraction is actually being dynamically adjusted to handle the water being drawn here. And we have a separate representation. We can see it right here of the ground. If I turn that into water, you'll gradually see that disappear, and just going into sort of a uniform representation of the water here. So we have, you know, I can go back and I could put trees in the middle. I could put a little island there or something. But anyway, so we have a very dynamic representation of the world. I can change it. And this is because we don't have quite the memory constraints that existed within Dragon Age. We can afford to have a little bit more of a dynamic representation. And so now I can change my world. As things change in the world, I can change what the pathfinding representation looks like. And I can start to represent these changes. And if the world changes, I knock down trees or make other changes, then I can have that be represented and reflected in the pathfinding itself. So what that means now is, in particular, is now my representation is sort of rich. And now you can think about, well, I have a character in the world. Let's just say I have a human, and I want my humans, oops, okay, I just messed that all up. I forgot to say that I was finding paths. So let me go back and recover my path in here. Sorry, there's my path going up there and my path here. Okay, so we're going to do finding paths. If I'm a human that's finding paths through the world, And
Sorry,
all
Nathan, when you say your path there, that's like a path meaning like cobblestone in the world,
it's a
not
road.
so it's
Yeah,
not
so
a not pathfinding path.
it's not a
Okay.
pathfinding path, but it's a road. And so you could imagine that, for instance, I have a vehicle that needs to travel through the world. The vehicle cannot go across water. The vehicle needs to travel on the road. If it has to go off road, it'd prefer to be on this open terrain. Maybe trees are, marginally passable, but there's no way it can go through water. So with a representation like this, what we can do in the abstraction is we can say, look, I'm going to go into this high level representation and do pathfinding and basically say, well, you can't go into water. So water, it's given a cost that's basically prohibitively expensive. I can say that by far the cheapest thing to do is to go on this road. And that means that when I ask you to find a path, the path you're going to find, and this is just showing like the optimal path versus the path that we get from the abstraction. The path we get goes straight down the road here. But you could imagine that I have something like deer, and there's no, so I go back here. We could have deer, and my deer may actually not want to be on the road. So actually, I don't know what's going to happen here. Good. Okay. So what we see here is the deer maybe feel like a road is a dangerous place. I mean, this is just a designer constraint.
Mm-hmm.
So the deer would prefer to go off into the forest. And if they're going to go between two locations, they're going to try and go through the forest and instead of trying to stay on the road. And so that's just going to, it's this thing where we can change the behavior that we get from the pathfinding at a very, very low level behavior. And so, this is really going to change. Like now, what can I do as an AI designer? Well, the fact that my pathfinding system supports this gives me a lot of rich primitives for creating a pathfinding system. And just to say, if I have a spell that lets me walk on water, we say, Jesus can walk on water. So here we go. Actually here. So we have this is probably a slight variance in costs here. Whether I walk along the path, there's probably a very minimal distance here. Yeah, so this is one of these like borderline cases. Is it shorter to walk straight across or walk across the road? But what we can see here is I can have this ability to walk, to say I should just walk straight across the water, or should I try and walk along on the path? And so I can change these costs. I can, and I'm going to get very different behavior without having to redesign my pathfinding system, because at the lowest level, these primitives are incorporated into the pathfinding that we're doing.
So there it says cost model. So this is not a constraint based thing. You are just modifying your cost, and the developer might be able to go and say make a new one where forest is 5 times the cost of road or something like that. Is that how it's sort of being done?
Exactly. So you could imagine that there's a giant, and you say, well, the giant can't walk through. There's a giant in the trailers for Nightingale. We might say, and actually, I don't know what the designers have done on some of these low-level details, but we say, the giants don't really want to walk through the forest. So they're going to try and find a path that doesn't have to go through the forest. Things like this are things that now you can say, this is the behavior that I want in general, and you can just any two characters, we can use the same pathfinding representation, but we can change a cost model, which will vastly change the behavior that we get.
That's awesome. That seems like it's really powerful, and also something that's important is it's very designer friendly. Like you don't need to go in and reprogram things if they want a new model, which is really nice.
Exactly, and then if I'm looking at my behavior, of course, we can tune the costs. But it means that, for instance, if I want you to just stay on roads, that's all I want you to do, then I can put in a cost model that basically says, you're just going to stay on roads here. And actually, so there is a video here that talks a little bit about this in more detail.
That's great. One thing that I wanted to ask, which may or may not be in this engine or other pathfinding engines you've done, something that we run into in StarCraft all the time is like units getting stuck on each other, right? So for a system like this, would you be able to modify something like this so that, say, if a giant is in the middle of the road, the pathfinding system would actually take that as an obstacle? Or is it just looking at the environment versus other NPCs in the environment? And that problem as a whole versus this dynamic can't run into other entities or sort of deal with that when you get to it sort of behavior like StarCraft has.
Yeah, so a thing there, which is that, what is dynamic in the world, and I want to, it really shouldn't be involved in pathfinding because it might change by the time I get there. What's static that I should really consider when I'm doing my pathfinding is a hard question, and maybe one that there isn't ever actually a really good answer. But the solution to something like this, like something like a giant, is that you use one of these local avoidance techniques. So there's a technique that I really like by Stephen Guy, and there's an article about it in Game AI Pro, one of the Game AI Pro books. And so that's freely available, and he's got pseudocode in there that implements it really well. And as a technique, what that does is basically says you look at the time to collision between you and the characters around you. And then based on the time to collision, you can create an avoidance force that is then applied to your path. And so if there was a giant standing here and you were trying to walk, and that went right through your path, basically the steering component in the world would apply a force to cause you to walk around that giant. What's really neat about this approach is actually you can tune some of the parameters of how far I look ahead, how much of a force I want to apply. And so you could do this for things like powerful creatures in the game. They have really small radiuses of where they consider that they should start to avoiding other characters. And if they have a smaller radius than everybody else, then everyone's going to start avoiding them before they start avoiding other people. And now you can get this really interesting emergent behavior where powerful characters are sort of everybody runs away from them or gets out of their way much more quickly than they try and get out of your way. And then you can start to get some really interesting behavior coming out of that from these sort of local avoidance systems.
That's really fun. On that note, you just reminded me of so one of my students who graduated recently, Lucas. One of his thesis was the main thing he did was, so in StarCraft, sometimes you want to do these sort of sneaky drop attacks. So you load up some units in a drop ship and try and sneak around the backside of the opponent's base. And so what we did in that case was we used A-star, but part of the cost function was actually an influence map based on vision. And so we said that the first thing you want to do is avoid the enemy vision if at all possible. And then only at, if there's no other way to get to your goal, do you then actually let yourself be seen. And so, influence maps and steering and stuff like that, that can all be used to avoid the dynamic pathfinding problem and sort of make it a path following problem, I guess, or a bit of a combination of both.
Yeah, just to say, there's a couple of papers that have been published about thinking about these sort of relationship models and how we want to move, like avoiding being seen and stuff like that. And for instance, if we look at this abstraction, so that can be expensive to compute that. But if you look at the abstraction, something that you could do is you could actually say, look, here's all the cells where nobody can see you. And here's the cells where you can be seen. And then you could imagine doing path planning where you say, look, at the high level, I'm going to go through these cells where I can't be seen as much as possible. And then I'm going to minimize going through the ones where I can be seen. And that's going to give you something like that much cheaper than trying to do every step of the pathfinding along the way. So just to say, in something like that, there's really some interesting trade-offs that could be done. And thinking about what is first class in my representation? If visibility is something that you really want to encode, you need to think about, when I design my representation, how do I ensure that that information is available so that it can be used by higher level systems that want to be able to reason about the terrain.
Yeah, it's a lot to think about, and it's really cool that you get to apply this sort of thing to a real game rather than just write papers about it.
Yeah.
So yeah, we're coming up on almost an hour here now. Last thing I like to ask the guests, unless you had more to talk about, was sort of if you have any advice. There's a lot of students in this course always ask me about things like, getting into the game industry or game AI programming, or what their portfolio might look like. Do you have any advice for people on sort of what skills they might want to have going into a game AI job? Like, do they need a lot of low-level programming, or algorithms more important, or what have you found to be successful tools to have in your toolbox when applying for these sorts of jobs?
Yeah, that's a really good question, and it's going to depend on the industry that you're thinking about working in. So in some places in industry, they're going to say, we absolutely need C++ with the ability to look at assembly and to understand that, to be able to do low-level optimizations. especially when you're thinking about something like a studio that's owned by something like Sony, where you're doing, first party titles. So you're thinking about like, am I developing something that's directly optimized for the PlayStation or directly optimized for the Xbox? Then some of those things might be really important. But you might be thinking about something that's, no, this is a web deployed game, and you're going to have very different constraints there. So you have to be a little bit cognizant of, what part of industry are you thinking about going to, what is important in that part of industry. But if we're thinking about programming, then it's very good to have, a knowledge of what is all the levels of the architecture, how do they interact, what are the things that are expensive, what are the things that are cheap. So having that knowledge is going to help you be able to write efficient code. If you're trying to write like a AAA title, then those become extremely important in getting the performance that you want. But in terms of getting noticed, actually, we had an interview last week in my class with Aaron Flynn, who's the CEO of Inflection Games. And the thing that he said that was really important is that he said the one piece of advice he gave to all the students was finish things. So whatever you're working on, show that you can finish things. And that means finishing your degree, finishing your thesis. It means finishing your classes. Like just showing that you have the capability to finish things becomes really important, because in a game studio, they need people who are going to be successful and finish things in that way. The other thing, a piece of advice I would give is you want to find ways to show that this is something you care about. So that's something you're trying to improve your skills, right? You wouldn't ever go say, well, this is, like I want to be an artist, but I refuse to practice art outside of my classes or something like this. Like if something you want to get good at, then your class is actually a means for improving what you want to be good at. They're not like the end goal is not your classes. So if you're wanting to be a good programmer to, build games, then you need to show that actually that's what your motivation is. Your classes are assisting you in that, but the classes in themselves are not like, that's not the end goal. The end goal is that you want to learn the skills that you need to learn to be able to do these things. And so then the question is like, what are you doing to show that you are interested in these things, that you're learning about these things? Are you creating complete tech demos? Are you, building something that just like has all the latest AI algorithms in it because you wanted to understand how they worked? But build something that you can complete, that you can show off, that demonstrates that you're interested in learning and you're passionate about learning because of your interest in some particular area. There's maybe a lot more that could be said there, but I think that'd be a high level. And there's of course many caveats to that as well. But as I said, that's a high level view of finish things and put together, do things. If you really are passionate about it, then it should mean that you're trying to learn on your own. That classes again are only a means to the end; they're not the end of themselves.
Awesome. Well, that's some pretty great advice to end on. If you had anything else, I think, are you think you're finished with talking about the pathfinding system?
I mean, I could talk for hours about it, but I think this is just to say, here's a brief glimpse of some of the things that we've been thinking about. And maybe as the game gets closer to ship, there might be some other things that we'll talk about more. And but I think for right now, that gives sort of this high level overview of what we're thinking about as we design the pathfinding, and now we're sort of designing the character behavior and other pieces to go with the low level pathfinding.
And just to remind people that if this is something that really interests you, there's professors out there like myself and Nathan who are always looking for enthusiastic grad students to work on stuff like this. So if this sort of thing is up your alley, then you could literally get paid to go to school to work on problems like this. So just keep that in mind. And grad school isn't just for like, Einsteins. It's for people like myself who kind of, didn't have the best grades, but had a real passion for this sort of thing. And so, yeah, just keep that in mind for grad school as well.
And let me just say here, if you go to movingai.com, you can find, this is just one of many demos that I have of many, many different aspects of search algorithms. You can find lectures and quite a few materials there and other demos. So this might be something that if you go start looking at this material and you start to find it really interesting, then that means you might be interested in doing more advanced education on these sorts of topics.
Awesome. All right. Thanks, Nathan. I think we'll end it there, right exactly at the hour mark. Thanks so much for being a part of the class, and I think the students will really appreciate all that advice.
Thanks, and good luck to everybody, and glad to have the chance to share with you today.